So what we're going to go over today is celestial navigation. So in basically learning about 5 different concepts, we're going to, starting with lat and long, what the concept of the terrestrial and celestial sphere is. And then we'll talk about the concept of infinite distance and parallax. And we'll almost bring it home with how parallel lines behave mathematically. And then finally, we'll talk about lines of position. So to start out with, let's talk about latitude and longitude. So traditionally, when people look at the globe, there are parallels of latitude, and the center one, of course, is the equator. There are meridians of longitude, and for our purposes, we'll just the prime meridian is going to be goes through Greenwich, and then it goes 180 degrees to the west towards the international date line, and 180 degrees the other way, of course. It meets at the 180 degrees, which is international date line. And you got the equator, and then lines of parallels of latitude that go all the way north to the North Pole and the South Pole. A common misconception with latitude is that we take these parallel slices out of the world. We actually don't. What it is we measure we take a slice of the world, we cut it directly in half, it goes to the center of the earth, and then we'll say this is 0, 10, 20, 30, and so on, and then we draw lines through each one of them, and where they touch the world, that's where we're going to put the parallel of latitude. So when it gets to the top, these lines are equidistant. And of course, there's 90 degrees between this line and that line. And in each degree, so 1 degree equals 60 minutes of latitude. In each degree, there's 60 minutes, and they've calculated a nautical mile, so 1 nautical mile equals 1 minute of latitude. And that's very handy. Using this, we can calculate the circumference of the Earth if we wanted to, because we know there's 360 degrees all the way around, because remember, this is a slice of the Earth with the very center of the Earth exposed. We know that's 90 plus 90 plus 90 plus 90, well, obviously that's 360, times 60 miles a minute equals 2100, so 21,600 nautical miles for the circumference of the Earth. Now that's a handy concept because it basically means that if we know the angle between 2 points on Earth, and this angle cutting through the center of the Earth, we can actually measure that. If we know these degrees, we know that those degrees equate exactly into nautical miles, which we can plot if we have a known point. So that's concept number 1. Concept number 2 that we need to go over is the concept of the terrestrial and celestial spheres. So we have our terrestrial sphere, which is the Earth, of course, and at any point, an observer, we'll put him right here, can look up, and if he sees a star above him, some kind of a celestial body, then if you draw a line from that star through his head, through the ground, all the way to the center of the Earth, that line where the star meets his eyes and it goes straight down, if it's directly above him, this is called the ground position of that celestial body. Now, all the different stars and the celestial bodies in the sky, including the moon, the sun, all the planets, and the other 30 navigational stars, are all around the Earth at any one particular time. Each one of those positions, each one of those stars is so far away that it can be considered fixed in space at any particular time. And if you look up at if an observer is directly underneath one of those celestial bodies, that spot, that ground position, can be plotted. And it's plotted in something that we call the nautical almanac for every second of every minute of every day of every year. So if you have a time in universal coordinated time down to the second, we can know where the sun, the moon, the planets, and all 30 navigational stars are at any one point. And just tying it back to concept number one, we hinted that if you know the distance, the angular distance between a known point and you, then you can actually figure out the distance between those 2 points, and that's going to help us do a fix, which was what we're after. So that's concept number two. So you've got a terrestrial sphere, and then you've got a celestial sphere which goes around, and the celestial sphere is inside that sphere. So at any particular spot, straight down is a point where an object on the celestial sphere matches up with an object on the, or a ground position rather, on the terrestrial sphere. So let's take that into the third concept, which is the concept of infinite distance. Now this one's, we're gonna have to pull a little bit of math. So I'll explain it in two different ways. First, I'll explain it practically, and then I'll explain it mathematically. So here's the practical explanation. So if we have two observers, and they're looking at a apple. This observer observes it from this angle. This observer observes it from this direction. And this angle is, we'll just call this angle X. Now, what happens to that angle if it was closer? Or that object rather, if it was closer? Let's say it's right here. Now, this angle increases. That's a bigger angle than that one. If this apple was to move farther away, what's happening to the angle now? It's decreasing. So with every increase in distance away from the observer, this angle decreases. Now, let's say that the sun, for example, is basically 147 million kilometers away. And two observers on the Earth, let's just say they're 1,000 kilometers away. 147 million is the distance here. It's so far away that this object, if I was to relate it to where I was here, this object would be on the other side of the country, around Newfoundland. So now this apple is in Newfoundland. Picture which way these guys are looking to see that apple way off in Newfoundland. Newfoundland's so far away that it's almost like they're looking in the exact same direction. It's that far away. This angle is so small, and these lines are almost parallel. As a matter of fact, Newfoundland is so far away when you're looking at an apple that these lines can be almost considered to be that Newfoundland is an infinite distance away, and then these lines are parallel. Now, for the skeptics out there, I understand, and I can prove it mathematically as well. So now what we're going to do is we're going to take a point. So we're going to take observer 1 and down observer 2. And let's just say that they're 4 kilometers apart. And they're looking at, this guy's looking at an object that's 4 kilometers away. Now this guy's also looking at that same object. And we figured out, he's paced it off and he knows that that's 5.6 kilometers away. We're trying to figure out this angle for our purposes. So to do that, we use an inverse cosine of x, that angle, equals the adjacent angle, or adjacent side, and the hypotenuse. So this here is the hypotenuse, this is the adjacent. So if we plug in the numbers, we got 4 divided by 5.6, and we throw that into cosine, and we take, that comes out to an angle of 44.4 degrees. If we run the exact same math, and you can see the relationship between these two numbers. if you run the exact same math with an object that is, say, 8 kilometers away for the observer versus 9, so we'll just extend this. So now this is 8 kilometers, and this is 9 kilometers. And we run the same math, the angle comes out to 27.2. That's a big reduction, and we only doubled the distance. Didn't quite half this, but we doubled the distance, and the angle reduced quite a bit. Now, if you look at the sun, which is 147 million, the distance of that away, versus even if the two observers were, say, 1,000 miles or kilometers apart, that sun is so far away they can almost the angular difference between one observer and the other is so small mathematically that actually, if you run the same math, it comes out to 0.006 degrees. And you're like, wait a second, 0.6 degrees, that is a real number. That's going to show up if you can see it. Well, what if I told you that that's actually, you'd need 15,000 of these to equal 90 degrees. That's how small of an angular change we're talking about. And that's the sun. What if we looked at a star? Those are millions of light years away, not kilometers, but light years. That's a long way. So as a concept for celestial navigation, we assume that the celestial body is so far away that the lines coming at you are actually parallel. Now, the moon is a little bit closer, but we do have a correction for that we can do, a parallax correction. But for the sun and anything farther, which is 99% of our celestial bodies, we just consider them to be so far away that the distance is infinite and the light coming in is actually parallel. So one observer looks at the object from one angle, the other observer looks at it from the exact same angle relative to that observer. Parallel lines, completely parallel. So now let's go into our fourth concept, which is how parallel lines behave. So let's draw two lines. So this line and this line. Let's consider them perfectly parallel. Now let's draw a transverse line that cuts between them. So this angle is the same as this angle. This angle is the same as this angle. We can see that. And as a matter of fact, this angle here is a corresponding angle to this angle here. So these angles are the same. And these ones are the same. And that's how they relate to one another. This is a really important concept. So you get parallel lines, a transverse line that cuts between them at the same angle. These two angles are exactly the same mathematically. That's concept number 4. Now is where we get to the nuts and bolts of this thing. Now we're going to figure out lines of position. So let's say that we will draw a circle and we have an observer, a fellow right here at this point, okay? And he looks straight up above him. And he sees the sun. It's directly above him. Let's keep that line going all the way through the center of the earth. So the ground position of the sun is exactly at his position. Now let's say that we're out here somewhere. We don't know exactly where we are, but when we look at the sun is not this direction. This is actually really, really close. Remember, we're assuming the sun is so far away that it's an infinite distance. So where this line is a parallel line, we're going to look up at the sun and see it exactly parallel, like that. So even though there isn't two suns, There's actually one sun, but it's like 147 million kilometers that way. So it just looks like one, okay? So parallel lines. But now, because the Earth surface is curved, when you look straight up, obviously it goes at the bottom of your feet is the center of the Earth, and you look straight up. This is directly above you. So the sun is observed to be on this line, this distance, this angular distance. Well, what tool can we use to be able to measure this angle? If you said sextant, you're absolutely right. But there's one crucial piece of information that we need to measure this angle. We need to know where the horizon is. And the horizon, if this is a vertical line, the horizon is a horizontal line that cuts right across like this. Okay? So if we pull out our sextant and we take a shot, and we can see that the height of the sun is this angle. Let's just say that that's 50 degrees. The height of the sextant is 50 degrees, okay? Now, if we want to know a distance, if you recall from earlier, an angular distance between two spots on the Earth, if we know this inside angle right here, we can, it doesn't matter if it's this angle is the same as this angle, is the same as this angle, it doesn't matter. But at the surface of the Earth, 1 degree equals 60 minutes, and there's a mile a minute, so every degree is 60 nautical miles. Can you figure out how we can determine this inside angle right here using the concept of corresponding angles? That's right. This angle here, let's just call that A, is the same as this angle here. How do we figure out this angle here? Here's a horizontal line, here's a vertical line, and there's a transverse line through there, and that's 50 degrees. That's right, we take 90 degrees, because we know that's 90, minus 50 equals 40. So this here is 40 degrees. And if this distance, if this angle is 40, it doesn't matter where that angle is, we know that there's 40 degrees between these 2 points, and distance, angles are distance. So 40 degrees equals, let's see, so if you take 60 minutes times 40 degrees equals 2,400 nautical miles. So that this point and this point are 2,400 nautical miles apart. But what information does that really tell us, though, when you think about it? Because now we got the world, and we know that, let's just say for fun, that this was that ground position of the sun right here. And then we know there's a 2,400 nautical mile circle around that. We are on, this is a line of position, an LOP. But because it's the whole world, it's actually a big circle. It's not really a line, right? So we figured out that we're at that exact moment that we captured that site, we're along this line somewhere. Next is to get another line of position, we have to look at a different spot. So let's say that there was the ground position of a star was right here. We figured out that this is the distance around there. Well, now we know that we're anywhere along this line, but actually because we've drawn two, we're only at two, there's only two possibilities of where we are, either right here or right here. And if we had our dead reckoning position, because we're doing sites several times per day, if the weather's good, we're going to have a rough idea. Now these two lines, because this is the whole world, they're going to be like 1,000+ miles apart. So we're going to know where we're at. But if we did a third position, then with those three lines together, we are bang on. We know exactly where we are without a shadow of a doubt. The third line intersects and it confirms the other two, and then we have a fix. And a fix tells you where you were, not where you are. So this is positioning we're learning. The navigation is a completely different situation, but at least you know at a certain time you were exactly at a certain spot. And modern sextants, well, even a practice sextant can get it down to about 1 nautical mile to 2 nautical miles position. And in the ocean, that's not very good for a road, but in the ocean, that's a huge amount of distance. So that's really good. And how we practically do it is, because we don't actually have bring around a giant map of the whole world and we can draw these big circles, is they've done all kinds of calculations for us in something called the site reduction tables, where that big, huge circle that goes all the way around the world, if we zoom in, like hugely zoom in, instead of a circle, a curve like this, it'll actually be a line of position, an actual straight line. Because when we're looking at a very, very tight area of the map, that will it's just considered to be a straight line because the circle is so big, it goes all the way around the world almost. It's a huge circle. So taking that concept into account, what we do in celestial navigation is we try to figure out what our dead reckoning position is, and then we figure out an assumed position. So let's call this the AP, assumed position. It doesn't have to be at exactly where our dead reckoning position is. It can be close, but it's important that for this assumed position, we know using the tables exactly where a certain celestial body is going to be, and we can figure out, based on where we are, what the direction of that body is, from that ground position, from the assumed position is, which is called the azimuth. And then we also know that if the azimuth is a certain direction, then we know that that line, that LOP, is perpendicular to that line. And once we have that LOP drawn, we know that we're somewhere along this line of position. So that information in itself is useful because it tells you that we're anywhere along this line. But where? We need a second fix to get that. And there's 2 ways to get a second fix. You could shoot another celestial body like we did last time. And let's just say we do the assumed position, we figure it out, and then it's this direction at this far. So those lines intercept right here. So this is enough to get us a fix. But if we used a third line of position and we crossed over, then we'd have an absolutely amazing idea of where we're at, because the third line confirms the position of the other 2. Because it's all separate math, and that's exactly where we are. And there's one little neat trick you can use if you only have one celestial body, let's say the sun, it's really easy to shoot. So you get a line of position, an LOP, at some point in the morning, we'll say. And then later on, going a fixed distance, and which you use, you know how far you've gone using a log, and you all know the speed that you're going, and you know the direction that you're traveling in. Let's say later on, there's a line of position that puts right here to the same body. So say 4 hours later, this is the line of position that we're at. What we do is we take this first line of position that we took 4 hours earlier, and if we know the speed and the distance, what we do is we transfer that line and we move it that direction and that speed for that exact distance. And then we have our old LOP just shifted using dead reckoning to where the new LOP is, and then this gives us a fix, and this is called a running fix. So using those techniques is how we position ourselves celestially.